Hello, Mr. Trong. Welcome to the Jack Cobb Show, where today I'll be diving into the topic of computer science. The agenda for the day. I'll be starting off with SDLC diagrams and the waterfall process, then getting into the unified modeling language and its diagrams, and then wrapping everything up with a following program analysis component. Let's begin. Software Development Lifecycles, Section 1. A software development lifecycle ensures the reliability and strength of a program and its design. Let us first dive into a comparison here. If a program is like a McDonald's burger, the SDLC includes the explaining for the idea behind the burger, the recipe for the ingredients, the construction of the patty, the testing of the flavor, and finally, making sure the burgers keep being sold. There are a variety of different takes on SDLC processes as well. Processes include plans that resolve around proper organization and clear-cut design processing of a program, or to winging the production itself from the get-go. These processes include the following: the Big Bang model, an explosion of an idea that magically leads to fantastic software; a Scrum model, a method where a lot of things get a lot messy; and finally the Waterfall model, a sophisticated and proper design model of a program. I'll be getting into this model with more detail later in my presentation. Almost every SDLC process is split into different phases. Each phase is performed specifically before the next. The SDLC process starts with an analysis of the user requirements and ends with an operation and maintenance of the system itself. This is a diagram of a standard SDLC. Requirements gathering analysis, the pre-planning chapter or the first chapter of the cycle. This phase is incredibly necessary as it marks the beginning of the program design process. Expectations based on the client or the programming team need to be laid out and fully acknowledged before entering the design process for the program. To ensure everyone involved around the program is on the same page, the following activities can be performed: A. Capturing stakeholder requirements through surveys and interviews, and B. Creating prototypes or quick visual representations to showcase what the final product will look like for approval. Design, the planning chapter. The technical design requirements are laid out by the development staff, including architects and lead developers, software engineers basically. And there tends to be a business aspect alongside a program and a product. Requirements in terms of profit and efficiency are outlined to guide the application process of how the code will be written. On the flip side, technical requirements revolve around the addition of database tables, protection, and security services, and any new transactions that need to be defined. Hardware system requirements are also highlighted and brought under consideration. With the design step in SDLC, the following questions are emphasized throughout the process. A. Can external software programs undermine the security of the program? B. If the project is dealing with consumer privacy, is it possible to ask for a review with a legal department? C. What are the specific requirements and definitions of how the user should interact with the interface? D. How can the program be tweaked to make sure the functionality is fluid and fast? E. Is the program easily upgradable, allowing for new or replacing old features? And finally, F. Is the efficiency and speed of the program sufficient under user expectations? Coding, the construction chapter. After the multiple preparation phases, computer scientists actually begin coding and unit testing in this step of the process. Throughout long periods of coding and program construction, developers may demonstrate the current progress of the program to analysts. These analysts will determine whether or not the programming is meeting the wide variety of requirements explored before the coding process. Any newfound implications can be addressed as well in this phase of the SDLC process. The coding step is recognized as the most time-consuming component of producing software. However, the finished product is later put into a testing phase. Testing, the testing chapter. The program enters a testing environment where different methods of catching errors and recognizing design faults are all performed. System testing involves a program tester working to breaking the program through the perspective of a user. Sometimes, errors that were not thought possible are showcased and addressed through this step. Then, a user acceptance test, involving around many external users, determines whether or not the application meets their own personal expectations, which is very, very important. When all errors are fixed and expectations are met, all the parties involved in the production of the software eventually sign off and the actual deployment of the program begins. Exciting stuff. Implementation, deployment, the final chapter of the process. The size and magnitude of the application determines how much attention is needed to upkeep and continuously run the program without issues. On-call IT staff and other involved parties are employed to make sure everything functions smoothly. Any newfound errors or design issues are later addressed through system updates and reworks. So back to the waterfall model. It was introduced by Dr. Winston W. Royce, a fancy sounding name. It included the reorganization of former SDLC steps, as phases were instead cascading down rather than repeating in a cycle. However, system engineering, analysis, design, code testing, and maintenance components are all roughly the same phases that were presented in the previous SDLC cycle. Though, that being said, there are countless advantages to the waterfall model for program planning in specific, and these include A. Adaptation to shifting teams. Specific stages require specific employees, which allows the process to accustom to all kinds of workers. B. Focused structured organization. Every step along the way in a waterfall method process is part of a very well thought out plan. C. Accessibility for early design changes. Coding only begins after a lot of planning through a design procedure, as stated previously. And finally, D. Suited for milestone-focused development. Only one stage is underway at a time in a waterfall method, which allows for concentration on specific areas of the design process for the software. It essentially means that the final product is a lot more engineered. I can personally correlate the water model to the program I coded, Coplandia 4, The Hunt. I used a system engineering step to recognize the potential requirements of my application as I methodically wrote down my projection of the end product. Through an analysis phase, I restructured my thinking alongside what I believed was possible to code in my received timeframe. Afterwards, in a design process, I laid out my planning and decided which components I should code first. Then, of course, in a very lengthy coding phase, I got down to work and spent hours on hours creating code for my program. My testing was thoughtfully spread out across my coding components as I made sure I had solid foundation to build more code upon. Finally, I played my game many times to determine whether or not the game was too much of a challenge or too little, and I tweaked certain elements to what I thought would be best fit for an engaging user experience. Here wraps up section 1 of my presentation, SDLC diagrams. Unified Modeling Language, section 2. UML stands for Unified Modeling Language. The language was created consisting of many set diagrams to help develop pieces of software and make the lives of software developers and system developers much easier. The contained diagrams are based on the best software engineering practices that have been refined over many decades and proven to be very successful. In essence, UML diagrams can be used for anything, but they are certainly used by software engineers and computer scientists when organizing the coding process of a program. Unlike English or French, UML is a language that uses pictures and diagrams rather than words. It is universal too, which means certain symbols and diagram components are recognized around the globe. The original goal for the UML was to provide a useful organizational tool when utilizing object-oriented programming. The language itself has a rich, complex, and vibrant history. In 1996, a request was issued by the Object Management Group, or OMG, to group specific organizations under one task of creating a singular common diagram language. Many tech giants at the time worked together to produce a working UML 1.0 definition. These companies included and ranged from IBM, Microsoft, HP, to Oracle. Across the years leading to the 21st century, more companies joined the effort until UML hit version 2.5 to date. Now the language is one of the most important components in design and application processes for software development. There are a wide range of systems and symbols and diagram features that establish well-flowing and designed charts. These include the following. A class is presented through a singular box filled with 3 components, important components at that. The first segment presents the class's name, so whatever the class is called is in this box, which is in italics if the class is abstract. If a class is abstract, then no instance of that class can be created, and it relies heavily on its subclasses. The second segment outlines all the class's attributes and variables. A minus sign represents the privacy of the variable, as each variable is highlighted with a name and a type. On the topic of encapsulation, a minus sign means the variable is private, a plus sign means the variable is public. The third and final component includes all the methods inside the class. They can be either private or public, or protected, as well as variables and other characteristics of the class. Inheritance is marked by a regular line with an empty arrowhead at the parent class. It presents how subclasses inherit the attributes presented in the parent or superclass. In this example, the animal class extends its attributes down to the tortoise class, otter class, and the slow loris class. Association is marked by a regular straight line. It showcases that one class has a direct relationship with another class. For example, otters eat sea urchins. Depicted through the UML language, this relationship is solely involved with the otter and sea urchin classes. Aggregation is a special relationship between two classes that is marked by an empty diamond. It means that one class can exist inside another, but does not have to. In this example, a creep is made of many tortoises. A creep is a plural for a group of tortoise, right? However, a singular tortoise can live by its own. This is an example of aggregation, and it's an important relationship inside the UML process. Composition is another relationship between two classes that is marked with a full diamond, a diamond that is full in. It acts in a way opposite to that of an aggregation relationship, as one class exists dependent on the existence of another class. For example, a bathroom in this case cannot exist without a visitor center, so the relationship is marked with a composition diamond. So what's important? Well, there are many examples of the different components UML covers as a visual language. Incredibly well-organized software systems can be laid out through the use of UML before the actual coding process begins, which is very important. Why is UML incredibly important, however, and used on a regular basis? Well, A, it's simple to use and understand, and there are many pieces of online software that allow diagrams to be created. However, it is convenient because it can also be drawn on paper or on a note. B, it provides a variety of mechanisms that relate to the core concepts of a soon-to-be-produced program. C, it can be used across the board in multiple different types of object-oriented programming languages. D, fundamentally, UML is incredibly basic. However, its variety of functions can be accessed to create highly complicated and sophisticated frameworks of advanced software programs, which is why UML is heavily used when a large project or program needs to be created. In conclusion, many different concepts in object-oriented programming can be visually represented in a planning process. Program analysis. Section 3. Program analysis is the idea of either automatically or manually reviewing the output of computer programs under lenses revolving around correctness, robustness, safety, and liveness. All of these individual lenses, of course, fall under two major brackets. First off, program optimization, where there's a focus on the efficiency of a program and how quickly it can run. This also puts an emphasis on the amount of resources used, based on the hardware which is associated with the software. Program correctness is including making sure the program does what it's supposed to do. This is dependent on testing processes in the production of a program and the design phase. It correlates with assertions, which I'll get to later. As for how program analysis is performed alongside the construction of operation of a function, there are two different methods. First of all, A, static program analysis, where the program is analyzed while executing the program. B, dynamic program analysis, where the program is analyzed during runtime. This method is perhaps more accurate as it is more often than not functioning. Assertions are special pieces of code that enable programmers to ensure the functionality and security of their program. Assertions are incredibly good examples of defensive programming. Programmers write statements of assertions at either the beginning of a computation or at the end of a computation. Their main purpose is to make sure that assumptions on functions or components of a program are exactly what the programmer expects them to be. In computer programming, an assertion is a statement where its boolean is evaluated to be true or false. If the boolean is true, the code runs as normal unless there's a proper runtime error. However, if the boolean is false, an assertion failure results and the program crashes unless there's an assertion exception. For example, There are two assertion statements displayed, and both are true. In the first statement, the code passes as x is 1, which is greater than 0, and in the second statement, x is 2, which is greater than 1. Let us say, though, that the first assertion statement read assert x greater than 1, then the program would crash, if specified, right at that point. Assertions are therefore used to promote program correctness. A precondition is when an assertion is specified at the beginning of a computation, whilst the postcondition is specified at the end or aftermath of a computation. In other words, assertions that are preconditions deal with what tend to be inputted values, whilst postconditions deal with outputted values. Preconditions and postconditions themselves are also seen on AP exam questions as specific values entered into methods, parameters, and/or the correlated outputted result. To summarize, these two types of conditions can live outside of the assertion seen as just expectations for a method of segment of code. In a way, assertion acts inside dynamic program analysis as it catches errors or unintentional values during the run of a program. With thorough use of assertion, computer scientists can ensure that they have a solid foundation of code to rely on. Catching errors through this procedure early allows for a lot more time to be saved, and ultimately, a lot less frustration. As explained, assertion deals with the correctness of a program. However, different types of efficiency deal with program optimization. These types include the following efficiencies revolving around computer science. A. Algorithmic efficiency, which includes enhancing the speed and shrinking the memory necessity of a program. B. Storage efficiency, which analyzes the effectiveness of a computer programming storage. And C. Last but not least, efficiency factor, which deals with data communications. The algorithmic efficiency of a program is related to the general productivity of a certain piece of code. It is crucially important and dependent on the amount of work processed through the code by the hardware. For example, a code that runs a total of 1 second is very slow. It has to run 1,000 times. It's self-explanatory. As a result, algorithmic efficiency deals with the capable benchmarks of a function or method. Whether these benchmarks include high run speeds or minimum memory usage, the programmer has to understand which requirement to focus on. Obviously, memory, for example, is linked to the hardware used for a program to run. Over the years, computer scientists have put together code for many different sorting algorithms. For example, two common algorithms are merge and sort. In the worst case scenario, selected sort could run n to the 2 times, where n is the amount of inputted data. On the other hand, merge sort would run n log n times as a worst case scenario, which is a much smaller value. In this specific example, it is obvious that selected sort is a lot less efficient than merge sort. It goes to show how different algorithms can play large roles in the overall efficiency of a program. This is why computer scientists are constantly designing new algorithms. From another lens, the overall efficiency of a program is also reliant on the storage efficiency, which is the capability of a program to store and access data. The idea is for a program to consume the smallest amount of space in memory, with no drastic alteration to function of the program itself. The Storage Industry Networking Association, or SNIA, defines efficiency as the following. Storage efficiency equals effective capacity plus free capacity over raw capacity. Methods for increasing the storage efficiency include the following. A. Snapshot, which allows for the same data to be reused for potentially different reasons. B. Data deduplication, which locates duplicate pockets of information inside a program and remove them, freeing more memory as a result. And C. The last method is thin provisioning, a function or a method that allows allocated memory that is unused to be shared among users. The last point is crucial in terms of software with high demand. And lastly, we have the efficiency factor of a program. And it's not necessarily a type of form of efficiency, however, it's a very important marker for how efficient a program is and is crucial when accessing the program's optimization. The factor is a ratio that compares the time it takes for a program to perform a function to an expected specified value of time. The significance of the efficiency factor is down to the comprehensible logic behind the index and how accessible and easy it is to use. This concludes the types of efficiency and how they are all vital under acknowledging the overall efficiency and optimization of a program. To conclude though, program analysis is a very important component of software design. The two components of program analysis, program optimization and program correctness, are crucial when evaluating the overall successfulness of a program. Procedures such as a thoughtful use of assertion and thorough contemplation of efficiency allow for software today to integrate into society and solve the world's greatest challenges. Thank you so much, Mr. Trong, for watching my presentation and my quick dive into some very important topics in the field of computer science. All I have to say is, tune in next time.